that forms the input to the amplifier, that is Vi. So Vi is Vs minus of Vf, and that is given to the amplifier. The amplifier amplifies the input, and that is given as V0. In turn, a portion of the V0, that is Vf, is once again fed back. So this process continues. Now here, based on what is the sign of the Vf, whether it is positive or negative, based on that, the feedback can be of two types. One is the positive feedback, the other one is the negative feedback. That is, whenever Vf is negative, the feedback is negative feedback. That means Vs, that is the input signal, and the feedback signal, they have a phase difference of 180 degrees. So when I say Vf is negative, that means Vf is having a phase difference of 180 degrees with respect to Vs. So then that becomes a negative feedback. Now, positive feedback means whenever Vf is positive, that means the input signal Vs and the feedback signal Vf, they are in phase. So that's why we say when Vf is positive, the feedback is positive feedback. Now, when we use positive feedback and when we use negative feedback. So for all amplification purposes, we use negative feedback. And whenever you want to design an oscillator, so for getting oscillations from the circuit, we use positive feedback. So for amplification, it is negative feedback, and for oscillations, it is positive feedback. Now, whenever you give, now we'll concentrate on the negative feedback. Further, we'll study about the positive feedback. So with negative feedback, the overall gain of the amplifier will reduce. But still, there are many advantages of going for negative feedback. So let us see what are the advantages of negative feedback. So here are the few advantages of negative feedback. Better input impedance, okay, better stabilized voltage gain, improved frequency response, lower output impedance, reduced noise, and more linear operation. So I'll explain you all this. Now you all know that I told you about amplifiers earlier when talking about operational amplifier. Then I told for any amplifier to produce the good output, it should have a very high gain, higher input impedance, and lower output impedance. So all those parameters are also added here. So they are also the advantages of the negative feedback. Okay, so let us see one by one here. Now, what are the advantages of going for negative feedback? I can also say what are the properties of negative feedback amplifier. So it is desensitizing the gain. That means what? It is bringing the stability. So it is maintaining the stability of the amplifier. That's what I told here. Better stabilized voltage gain. What do you mean by better stabilized voltage gain? See, whenever you design an amplifier for a particular gain, okay, that gain has to be less sensitive towards the various parameters that may affect it. Okay, so whenever you design a circuit, there are so many other external parameters that may affect the performance of the circuit. So when these act on the circuit, the performance of the circuit can come down, the gain of the circuit can come down. Okay, so in order to avoid that, what we do is we go for negative feedback, where this makes gain less sensitive to all kind of variations. That means though there are other parameters which may tend to decrease the gain, but still by using the negative feedback, we can make it less sensitive. That means the variation becomes very less. Okay, so this is how you can bring the stability. Stability is you maintain the gain of the amplifier irrespective of the kind of variations they are applying on the circuit. Okay, like reduce non-linear distortion. Now, whenever you design an amplifier, it should work linearly. Work linearly in the sense the variation in the output should cause the same variation in the output. That means the circuit is working linearly. But sometimes it may become non-linear. That means what? The variation in the input is not same as the variation in the output. So we can go for negative amplifier, so that negative amplifier, when I say, I'm sorry, when I say negative amplifier, it is, I'm talking about negative feedback. Okay, so whenever we go for negative feedback, that negative feedback makes the output proportional to the input. That is what I mean. Proportional means the variation in the input should be same as variation in the output. So we are trying to reduce that non-linear distortion if we are going for negative feedback. And the other parameters that affect the amplifier is the noise. Okay, so when you design a circuit, the noise will come into picture. It may enter into your circuit, and that may result in the degradation of the performance of the circuit. Okay, the noise can be the external noise or the noise within the circuit. Noise, we call it as unwanted electric signal. So with negative feedback, you can try to reduce the effect of noise. Actually, you cannot nullify it, because there is always the presence of noise. You cannot make it zero. But what we can do is we can try to reduce the effect of noise. Next, we want our amplifier to have high input impedance and low output impedance. So these variations, like whether I can increase or decrease this input and output impedance, that can be done. That means it can be controlled by using negative feedback. The next important thing is bandwidth of operation. Usually, we design a circuit such that it provides a good bandwidth. So with negative feedback, you can extend the bandwidth of the amplifier. Bandwidth of amplifier is nothing but a range of frequencies for which your circuit provides a satisfactory response. Okay, so you can always go for extending the bandwidth of the amplifier with negative feedback. So these are some of the advantages, or I can say properties of negative feedback amplifier. Now when you refer to the first circuit, I showed you, this is the typical feedback connection where we take a portion of the output. We take a portion of the output and we feed that to the input. Now based on, when I say portion of the output, so what portion of the output you are taking to feed it back, whether you are taking the voltage or whether you are taking the current, and when you are feeding it back to the input, how are you connecting this feedback with the input? Whether you are connecting this feedback signal with the input serially, or you are connecting this feedback signal to the input signal parallelly. So based on this, you have 4 feedback connections. Okay, so I told you, like when you are taking the feedback signal from the output, what feedback signal are you taking? Are you taking the voltage from the output, or are you taking the current? And when you are feeding it to the input, okay, to get mixed here, whether you are feeding it in series with the input or in parallel with the input. So based on this, you have 4 types of feedback connections, and they are voltage series feedback, voltage shunt feedback, current series feedback, and current shunt feedback. Now in these 4 types, the first term indicates what type of signal are you taking from the output for feeding back, whether you are taking the voltage signal or you are taking the current signal. And the second term in this types of feedback indicates whether the feedback signal is connected in series at the input side, or it is connected in shunt. Okay, so based on that, you have 4 feedback connection types. So each one has its own advantage. Now as per your syllabus, you are going to study about voltage series feedback amplifier. Okay, so let us continue further. So the same thing, whatever I told earlier, the same thing I have written here. So as I told, voltage refers to connecting the output voltage as input to the feedback network. Now current refers to taking the output current for feeding back, and series refers to connecting the feedback signal in series with the input. I told you series refers like how are you connecting the feedback signal to the input, and shunt refers to connecting the feedback signal in parallel with the input, so source. Okay, and what is the advantage of going for series feedback? Okay, series feedback tend to increase the input resistance, that is input impedance, and if you go for shunt type of feedback, it will tend to decrease the input impedance. And if you are going for voltage feedback, it will decrease the output impedance, and if you are going for current feedback, it will increase the output impedance. Now what is your requirement? So based on that, you can select what type of feedback you want. Okay, and we'll be concentrating on voltage series feedback type, voltage series feedback amplifier. So this circuit shows the voltage series feedback amplifier. So observe clearly. So the first circuit, whatever I showed, the same thing is being redrawn here. Okay, indicating all the voltages at different levels. Right. So this is our input, which is PS. Okay, and this is the amplifier in the forward path. Fine. So A is the gain of the amplifier. The input to this amplifier is Vi, and the output of this amplifier is V0. So where are we measuring V0? Across RL. And this part refers to the feedback part. Okay, so this is the feedback. So the feedback element is denoted by beta. So beta indicates the feedback. That is what, when you are taking the part of the output signal, what part of the output signal you are taking and feeding back. So it is beta. So here it is, this circuit is voltage series feedback amplifier. So I already told you previously what is the meaning of the first element in this and what is the meaning of the second element. So voltage series means we are taking the output voltage for feeding to the input. So you can see here. So I am taking output voltage. So this, by using these two lines, indicates that I'm taking the output voltage. So whenever we take the output voltage, we have to take it parallelly. How do you measure the output voltage? Parallelly, right? Okay, so output voltage is being taken. So what for output voltage is V0, right? What portion of V0 is fed to the input source? Beta times V0. That's what I told. Beta is the feedback factor. So how much of V0 is fed back to the input? Beta times V0 is fed back to the input. And that beta times V0 becomes the feedback signal, right? And that is indicated by VF. VF stands for the feedback voltage. Okay. And how much feedback voltage are you giving to the input? Beta times V0. And this feedback voltage is connected in series with the input. So this connection here indicates that it is a series connection. Okay, so that's why it is voltage series. Okay, and observe one more thing here. So this amplifier, this amplifier where I've indicated, I'm showing here, this amplifier has a gain of A. The input to this amplifier is Vi, and the output to this amplifier is V0. So when you don't have any feedback, then Vi will be same as Vs. Okay, so whenever you give feedback, then feedback will also come into picture. Then Vi becomes Vs minus of Vf. Vi becomes Vs minus of Vf with feedback. When there is no feedback, Vi is equal to Vs. Now let us understand, if we are going for voltage series feedback amplifier, what are the changes that you can find out? Like the changes in the gain, changes in the input impedance, change in the output impedance, and how can you maintain the stability of gain when you are going for voltage series feedback amplifier. So first let us see what will happen to the gain of the amplifier when you are going for voltage series feedback. So to indicate that, we have A and AF. So here A indicates the gain of the amplifier without feedback, and AF indicates the gain of the amplifier with feedback. So let us understand what is their relation. Okay. So refer to this figure always. Yeah. So as I've indicated here, the gain of the amplifier is A, which is equal to V naught divided by Vi. So I've written here A is equal to V naught divided by Vi. Fine. So we have A is equal to V naught divided by Vi. Now, when there is no feedback, then Vf is equal to 0, right? Yes. Then Vf is equal to 0. If you refer this figure, we see that as per this figure, Vi is equal to Vs minus Vf, where Vi is equal to Vs minus Vf. So when there is no feedback, Vf is equal to 0. So Vi is equal to Vs. So that's why I've written here A is equal to V naught divided by Vs. So this is when there is no feedback. Now we are trying to understand what will happen to the gain when we give feedback. Okay, second case, if feedback signal is given. Okay, so if feedback signal is given, then we substitute Vi is equal to Vs minus Vf. So I have A here, which is V naught divided by Vi. Okay, so V naught divided by Vi with feedback. Vi is equal to Vs minus of Vf. So substitute. So I get V naught divided by Vs minus of Vf. So V naught is equal to A into Vs minus of Vf. That is what is being written here. V naught is equal to A into Vs minus of Vf. Okay. Now if you open this bracket, so I get A into Vs minus A into Vf. Fine. So I get V naught is equal to A into Vs minus A into, what is Vf? Vf is the feedback signal, which is beta times V naught. So A into Vs minus A into beta times V naught. Fine. Okay. So then completely, if you remove this bracket, we have V naught is equal to A into Vs minus A into beta times V naught. Okay. Now we have separated the V naught terms and Vs terms. So if you take V naught as common, so I get 1 plus A beta is equal to A into Vs. So in this, you take the ratio of V naught divided by Vs. So V naught divided by Vs, you are getting it as A divided by 1 plus A beta. A divided by 1 plus A beta, where V naught by Vs. Once again, this is also the ratio of output voltage to the input voltage, but it is not V naught by Vi, it is V naught by Vs. So this is the gain with feedback, AF. So we got AF is equal to A divided by 1 plus A beta. That means what can you understand from this equation? From this equation, we understand that the gain with feedback is less when compared to gain without feedback. That means what? The gain is being reduced by a factor of 1 plus A beta. Earlier it was just A before giving the feedback. Now you give the feedback, it becomes A divided by 1 plus A beta. The gain is coming down. Okay. So I can say with feedback, the overall gain of the circuit is reduced by a factor of 1 plus A beta. So now this cannot be a disadvantage because though the overall gain is coming down, we have so many other advantages of having the negative feedback. So this is one parameter. Next, let us see the other parameter. Other parameter is nothing but the input impedance. So let us see how the input impedance will vary. Fine. So input impedance, it is the ratio of voltage to the current at the input side. Okay. So at the input side, your input voltage is Vi and the input current is Ii. So the ratio of them is the input impedance Zi. Okay, so Zi is given by Vi divided by Ii. Okay, or I can say Ii is equal to Vi divided by Zi. And you all know what is Vi? Vi is nothing but Vs minus Vf. Refer to this first figure. Okay, so Vi is nothing but Vs minus Vf. Fine, so we have substituted Vi is equal to Vs minus Vf divided by Zi. Fine. Now once again, Vf is the feedback signal that is given by beta times V naught. Right? So Ii is equal to Vs minus beta times V naught. Okay. So beta times Vf is substituted as beta times V naught. Fine. Once again, what is V naught? V naught is written in terms of AVI because we know that A is equal to V naught divided by Vi. So V naught is given as A into Vi. Yes. Okay. Now, so we have cross multiplied here. So I get Ii into Zi is equal to Vs minus of beta times A into Vi. Okay. Or I've taken all the other parameters to the right hand side and Vs is taken to the left hand side. So in this equation, I into Zi can be taken as common. So I get Ii into Zi. To take them as common, I get 1 plus A beta. Fine. So what is there on your left hand side? I have Vs. So Vs is equal to Ii into Zi into 1 plus A beta. So now I am trying to find out the input impedance, right? So I take the ratio of Vs divided by Ii. So which is equal to Zi into 1 plus A beta. So what is that I am getting here? Vs by Ii is equal to Zi into 1 plus A beta, where Vs by Ii is nothing but the input impedance with feedback. Vi by Ii is Zi, input impedance without feedback, whereas Vs by Ii is input impedance with feedback. Now, finally, I got Zif is equal to Zi into 1 plus A beta. Means what? The input impedance is improved by a factor of 1 plus A beta. Okay, so I can say Zif is increased. because it is Zi into 1 plus A beta. Okay, so the overall gain is getting reduced by a factor of 1 plus A beta, whereas the overall input impedance has improved by a factor of 1 plus A beta. Now let us check what happened to the output impedance. Okay. To find out the output impedance, so we have to do some changes to the circuit. What are the changes we do is we short the input voltage. We make Vs is equal to 0 and we apply a voltage V at the output, and that results in a current I. Where are we doing this? Please refer to this circuit here. Yes, in this circuit we are applying the voltage V at the output and we are making this Vs is equal to 0. So for simplification, I just showed you this output part. Okay. Yes. So we are applying the output voltage V that results in the current I. Okay, and we are making Vs is equal to 0 at the input. And this Z0 indicates the output impedance of the circuit. Now let us see what is the change that we expect when you are going for a negative feedback, whether output impedance increases or the output impedance decreases. Okay. Now to find that, let us apply KVL to this loop. So I am applying KVL to this loop. So when you apply KVL, you can see from this side I get V is equal to I into Z0. How many KVL is what? Sum of all the voltages in a loop should be equal to 0, right? So what are the different voltages you have in this loop? One is V, one is Z0 into I, the other one is A into Vi. So I get V is equal to I into Z0 plus A into Vi. Now, so this is the same equation what we have written here by applying the KVL. V is equal to I into Z0 plus A into V. Now we know that Vs is equal to 0, right? So we make Vs is equal to 0 in the equation of Vi. We all know Vi is equal to Vs minus Vf. So I make Vs is equal to 0. So I get Vi is equal to minus Vf. So let us substitute this in the given, the written KVL expression. Okay, so I get V is equal to I into Z0 minus A into, what is Vi? Minus Vf. Fine. So I get V is equal to I into Z0 minus Vf. What is Vf actually? The feedback voltage, if you remember, it is nothing but beta times naught. But where V naught is the output voltage. But at present, what is our output voltage? We are applying the voltage V at the output, right? So it is nothing but beta times V. So we have Vf is equal to beta times V. So we substitute Vf is equal to beta times V. So we have substituted. Now after that, all this V plus A beta V are separated, and on the other side we have I into Z0. So here we have taken V as common. So if you take V as common, I get 1 plus A beta. 1 plus A beta, which is equal to I into Z0. Now what are we trying to find out? Output impedance with feedback. Now I'll take what is the output voltage here? V. And what is the output current? I. So we take the ratio V by I. So when I take the ratio of V by I, from this equation, what is that I am getting? I am getting Z0 divided by 1 plus A beta. Fine. Where V by I is nothing but output impedance with feedback. So what can you infer from this? I can say that the output impedance with feedback is reduced. It's come down. Earlier, the output impedance was just Z0. Now with feedback, the output impedance has reduced. By what factor it has reduced? 1 plus A beta. Right? So with this, I can say whenever we are going for, now we are concentrating on what amplifier? We are concentrating on voltage series feedback amplifier. And what type of feedback we have taken? Negative feedback. So with this, we can say with this, the overall voltage gain of the amplifier is getting reduced by a factor of 1 plus A beta. The input impedance of the amplifier is improved by a factor of 1 plus A beta, whereas the output impedance of the amplifier is come down by a factor of 1 plus A beta. Now let us see stability. How is the stability in the gain maintained? As I told you, once you design an amplifier, the gain of the amplifier should be stable. That means the variations in the gain should be very, very less. Even though there are some other factors which are acting on the circuit. Okay. So irrespective of the variation, the variation in the gain should be very, very less. Only then we can get the stability. Otherwise, we can't get the stability. So how are you going to prove that? Okay. So to prove that, let us consider the relationship between AF and A. What is the relationship between AF and A? AF is equal to A divided by 1 plus A beta. You all know what do you mean by AF and what is A. AF is gain with feedback and A is gain without feedback. Beta is the feedback element. Now what we do is we differentiate this equation with respect to A. So when you differentiate, I get d by dA of AF, and here we have differentiated this equation. So you have to use this u by v method. So u by v method, v square 1 plus A beta the whole square. Then we keep b 1 plus A beta and differentiate u. That is differentiate A with respect to A. So I get 1 minus of then u, okay, that is A, and differentiate the denominator. So when I differentiate A into, when I differentiate the denominator, what I have? I have this constant. So differential of that is 0. And here if I differentiate A with respect to A, it is becoming 1. So I have only beta. And if you expand this, I get 1 plus A beta minus A beta. So A beta will get cancelled. So I have only 1. So 1 divided by 1 plus A beta the whole square. Okay. So I have d by dA of AF is equal to 1 by 1 plus A beta the whole square. Now what I do is I take this dA to the right hand side. So when I take dA to the right hand side, I get dAF is equal to dA by 1 plus A beta the whole square. Now I divide the complete equation by AF. So when I divide the complete equation by AF, so I get dAF by AF, and dA already I have 1 plus beta A the whole square into 1 divided by AF. Okay. So here I have dAF by AF is equal to dA by 1 plus A beta the whole square and 1 divided by AF. Okay. You know what is AF? AF is A by 1 plus A beta. So 1 divided by AF will be 1 plus A beta divided by A. And here 1 plus A beta once and 1 plus A beta once will get cancelled. So I am left with only 1 plus A beta. So I get dAF by AF is equal to, so these two I combine, dA by A into this 1 plus A beta. It has cancelled and I am left with 1 plus A beta, right? So 1 divided by 1 plus A beta. And in 1 plus A beta, usually this A beta it will be very much greater than 1. So I can neglect this one. So I have only A beta left. So finally I can say dAF by AF is equal to dA by A into 1 divided by A beta. So what can you understand from this? In this equation, if you observe, this element refers the variation in the gain with feedback. Okay, variation in the gain with feedback. Whereas this parameter indicates the variation in the gain without feedback. So this equation says that the variation in the gain with feedback is very less when compared to the variation in the gain without feedback, because see here, the variation in the gain dA by A is multiplied by 1 by A beta. That means this whole quantity is getting reduced because you are multiplying that by 1 divided by A beta. That means what? The variation in the gain with respect to feedback is less. Variation in the gain is less means what? The stability is maintained. The variation is less, so the gain is not changing in the amplifier after you design. That means the amplifier is able to maintain the stability in terms of the gain. So that is how the concept of negative feedback has this advantage. So it is trying to maintain the stability in gain. Next, there is another important factor. Now I told that the advantages of negative feedback amplifier. With negative feedback, the bandwidth will increase. Yes, the bandwidth will increase. The gain will reduce. Correct? Without feedback, the gain will be large. The bandwidth will be less. With feedback, the gain reduces. Already you have seen that the gain reduces, whereas bandwidth increases. Irrespective of this, if you take the product of gain and bandwidth for both the cases, they'll be always constant. That is what we are trying to understand here. Okay, so to understand that, let us take the frequency response of the amplifier. What is frequency response? It's very simple. Frequency response is nothing but a plot of gain versus frequency. See, once when you design an amplifier, okay, so when you design an amplifier, you'll be giving the input signal. You'll be giving the input signal for amplification, and those signal will have some frequency, right? So you'll be giving the input signal with different frequencies. So the variation in gain, okay, with respect to the frequency is being plotted here, and that is the frequency response. So you can see in this frequency response, you have two plots. One is the gain with feedback and the gain without feedback. Okay, so this is just a curve like this. Actually, when you do it practically, you will be getting this curve. Okay, so for an amplifier without feedback, okay, if you plot gain versus frequency, this is the plot you get, and this indicates the maximum gain you are getting. That is indicated as A naught. Okay, and for this, let us find out the bandwidth. What is bandwidth? The range of frequencies. So when I say range, it should have the upper cutoff and the lower cutoff. So let us identify upper cutoff and lower cutoff. So to identify, what we do is we multiply the highest gain by 0.707. So when I multiply the highest gain by 0.707, I get this point on this gain axis. So I'll extend the line such that it cuts the frequency response at 2 points. Okay, so this point will give me the lower cutoff frequency, and this point will give me the higher cutoff frequency. So bandwidth, this is the bandwidth. So we take the difference of these two frequencies, F2 minus of F1. So that will give me the bandwidth without feedback. Okay, now the bandwidth with feedback is this. So if you plot, the response is coming like this. Now you can observe from this plot with feedback, the gain has come down. Earlier it was A naught, right? Now the gain has come down. So I'm indicating this with A naught F. The gain has come down. But you can see the bandwidth has increased. So once again, to find out the bandwidth, we need upper cutoff and lower cutoff frequencies. So for that, we multiply 0.707 with A naught F. So when you multiply, this is the point I get on the y-axis. So if I extend this line, it's cutting the response at 2 points. So this is F2 and this is F1. F1F, that is feedback. F2F. The difference in F2F and F1F is the bandwidth. So you can see the bandwidth has increased. Now in this figure, you can see that F1 is very much lesser than F2. So I can say the bandwidth, which is the difference of these two frequencies, that is F2 minus of F1, I can say it is just F2. Can I say just F2? Because F1 is very much lesser than F2. Similarly, the bandwidth with feedback, also I can say F2F. Why? Because F1F is very much lesser than F2F. You can see this is the frequency. This is the frequency. I'm increasing the frequency from the lower frequency to the higher frequency. So F2F is large, F1F is very less. So I can say the bandwidth with feedback is F2F. Now when I take the product of this gain and bandwidth, usually, so when I take the product of A naught and this bandwidth without feedback, it will be same as A naught F into dWf. Why? Because here A naught is more and bandwidth is less. And here A naught is less and bandwidth is more. So the gain bandwidth product of the amplifier with feedback will be same as without feedback. Okay, so this was about, and this is very, very important. Fine. So you get this question repeatedly about the stability and about this gain bandwidth product. So this is what I am trying to write here. A naught into F2 is A naught F into F2F, where F2 is nothing but bandwidth. Because I told you here, F1 is very less, so F2 is bandwidth. Okay. So now based on this, we take a small example. There are many examples. I'll take one simple example. Yeah. So you have a question like this. Determine the voltage gain, input impedance. Determine the voltage gain, input impedance and output impedance with feedback for a voltage series feedback having a gain of -100, Ri of 10K, R0 of 20K. For feedback factor, beta is -0.1 and beta is -0.5. So very simple. So they have given you what is the gain before feedback, what is the input impedance before feedback, and what is the output impedance before feedback. So after feedback, what will happen, you have to find out. So you all know gain is A by 1 plus A beta. Now I have taken the first case. So let me look this. So I have taken the first case, that is when beta is equal to -0.1. So substitute A is -100, 1 plus beta is -0.1 into A is -100. So I get -100 by 11 minus 9.09. What was A earlier? -100. Okay, so now it is -9.09. Next is input impedance. So input impedance ZIF is ZI into 1 plus A beta, right? The input impedance will increase. So what is Zi given? 10 kilo ohm. 10 kilo ohm into 1 plus A beta. So already we have found out what is 1 plus A beta. It is 11. So I get 10 kilo ohm into 11, which is 110. So earlier it was 10, now it is 110. And what about the output impedance? So output impedance is Z0 divided by 1 plus A beta. So what was Z0? 20 kilo ohm. Okay. And 1 plus A beta is 11. So I get 1.82. Earlier it was what? 20. Now it is reduced to 1.82. Okay. And similarly, for the same data, we have calculated what is the gain, input impedance, and the output impedance for beta is equal to minus 0.5. So you can see that earlier the gain is minus 100, now it is minus 1.96, and the input impedance, it was 10 kilo ohm, right? Now it is 510 kilo ohm, and R0 20 kilo ohm, now it is 392.16 ohms, just ohms. So it has come down. Okay. So the rest is you have some more problems. So I'll be doing those problems in the next class.